Alright, so now I'm gonna derive the heat diffusion equation for spherical coordinates. So I have the sphere drawn here. This top part is going into the page, and this bottom part is like coming out. So first I'm gonna model the differential volume, which is dr d theta this is r d theta, and then r sine theta d phi. Alright, so the energy storage is density times the heat capacity times the volume, differential volume, which is r squared sine theta d theta d phi dr, and the energy generated is the flow rate generated times the differential volume, which is this. Alright, so now I'm going to calculate Q net, which is these three different volumes that I have highlighted. So the first one, we're going to start with the purple surface, which is Q net R. So this is QR minus QR plus DR. Now we're gonna calculate the Taylor series, which is QR minus QR minus the gradient of QR over QR times dr. And then this cancels out, so then you're gonna apply Fourier's law, which is the partial gradient of R negative K times the area the gradient temperature with respect to R dr, and the area for this is R sine theta d theta d phi. Kind of got squished there. Yeah, that looks better. Alright, and then what you're left with after canceling out is our temperature gradient with respect to R dr sine theta d theta d phi. Sorry, this is R squared. Alright, now we're gonna go on to the orange surface, which is Q theta starts off the same. The Taylor series now. Now applying Fourier's law. And you have to put R here because Fourier's law is in distance, not degree. And the area for the orange surface is R sine theta d phi dr. Yeah. So then that gives you, after it cancels, alright, and now we're going to go through the pink surface, which is Q net phi. And the same as before, this gets really repetitive. Now the Taylor series. The gradient of Q phi respect to phi d phi. Now applying Fourier's law. Oh, it goes on the bottom. Negative k times the area, the gradient of temperature over. So you have to put R sine theta d phi. Like again, Fourier's law is in distance, not in degrees. So that turns it to distance. D phi out here. And the area for this is R d theta dr. And after it cancels and simplifying, you get R, you get K, you get 1 over sine theta d theta d from dr. Alright, so now we're going to add everything together. So you get, based on the energy balance, you go this, is equal to Q net, which is all of these plus all right. Now we're going to cancel out the terms. So this cancels. Oh, forgot to bring over energy generated. Just barely fits. Okay. So these cancel out and these cancel out. All this cancels out. This cancels out and this cancels out. So for this one, you get an R squared added to it. And then you get, and then for the bottom one, and then this is squared. And for the bottom one, get 1 over R squared. Right, and then now we simplify. Oh, and then we also assume K is constant. So for that, we get get 1 over diffusivity times and then over K over the gradient of the temperature over phi. Plus sine theta plus Q over rho Cp. Oh, excuse me. So that is the thermal heat diffusion equation for cylindrical objects. Alright, so now I'm going to derive the thermal resistance for the spherical heat diffusion equation. So let's first start with the equation for the radical equation. Alright, and now let's simplify it. So it's a steady state. So then this can cancel out and this can cancel out. So then that gives us is equal to 0. And then we'll find the first derivative. So R is equal to C1. And now this is separable, so we can write it as this. And now we'll integrate from T1 to T2 and R1 to R2. So then that gives us delta T. And this side is negative C1 R1, and we'll R, and we'll do this from R equals R1. So then that gives us C1 being equal to 1 over R1 minus 1 over R2. And then we'll write this all together. So C1 is equal to delta T, 1 over R1 minus 1 over R2. And now we're going to relate this to resistance. So delta V is delta T, I is heat flow, times R, and we're finding R. So if we think of Q is negative heat conductivity times the area times the derivative of temperature with respect to R. So now we'll relate this to spherical, so it's negative K, and area is 4 pi R squared dr, and we're relating this to R is equal to R1. So then that gives us Q is equal to negative K 4 pi R1 squared. And we know dt dr is delta T over 1 over R1 minus 1 over R2 times 1 over R squared. And then these cancel out. So then that gives us Q is equal to K 4 pi delta T over 1 over R1 minus 1 over R2. So then turning this into this form, we get delta t equal to q times 1 over r1 minus 1 over r2 negative k for pi. So this is r.